In this paper, we introduce one-pointer RANSAC-based method to estimate the pose of an object on the ground from a monocular image. The perspective endpoint problem is one of the widely known traditional computer vision tasks. This task is to estimate a 6-degree of freedom pose parameter given a set of 3D points and their corresponding 2D points on the image. The PMP solver is widely used in many applications such as angle motion estimation, 3D reconstruction, object pose and shape estimation. In this paper, we consider the pose and shape estimation of on-load object as our target application. There are many existing PMP solvers. These are usually focusing on improving the accuracy from the noise data. However, the existing methods didn't handle the outlier contaminated data, so the existing solvers are very vulnerable to the outliers. In the literature, there are two schemes to handle the data with outliers. The first one is RANSAC-based scheme. RANSAC and minimal solvers are used to find the outliers and initialize your pose parameter. Then the initial pose is refined by the existing PMP solvers or a sort of optimizers. But depending on the minimal solvers, they have large time complexity, so it is a big burden on the devices for real-time applications. The second is the robust estimation-based scheme. This method iteratively reweight the point correspondences and recompute the pose until the convergence. So these are very fast and have a good accuracy. However, they are not robust to the data with a high ratio of outliers because of their statistical property. To solve this problem, in this paper, we propose a fast and robust pose estimation method. We adopt the RANSAC-based scheme because it is robust to the data with the high outlier ratio. First, I will introduce the perspective one-point algorithm as a very fast minimal solver. Second, the hierarchical robust estimation method to improve both the accuracy and robustness. To derive the PMP solution, we need to simplify the existing PMP problem. Basically, the 3D model and 2D 3D correspondences are given as input data in the existing PMP problem. To relax this problem, we use the additional information such as camera road geometry, on-road object assumption, and the 2D bounding box, which can be easily obtained in many practical applications such as ADAS or autonomous driving. Using this information, the PMP problem can be simplified as finding a key point depth and an object angle, which adjoin the object corners to both the left and right edges of the 2D bounding box on the bird's eye view. From the given data, we can derive the geometric relationship as shown in this picture. Here the yaw and depth values are only the unknown variables. Based on this relationship, we can derive a sort of equation for yaw and depth computation from a sine rule. Then the yaw angle and depth are calculated by the following expressions, and finally you can obtain the pose parameter from the yaw and depth estimates. According to the yaw angle, we can compute 4 solutions from one key point sample, but we can easily select a unique solution among them by considering the range of the angles as shown in the below table. The initial pose computed by the PMP solver can be optimized by minimizing the reprojection error of outliers. Moreover, we can use the M estimator to get more outliers and improve the accuracy. The proposed method can be expanded to simultaneous pose and shape estimation in a monocular image. In fact, this task is an ill-posed problem, but in the literature, many existing works have utilized active shape models to solve the problem. Using this shape model, the pose and shape are jointly estimated by minimizing the refraction errors. However, this approach still has some challenges. First, the PMP solver is sensitive to the noise pitch angle. Second, the robust estimator is sensitive to an initial pose estimate, and it is useless in the highly outlier contaminated data. Because the scale factor of the influence function is statistically estimated, so the M estimator doesn't work in the data with a high outlier ratio. To solve this problem, we proposed a hierarchical robust estimator which works in a cost-effective manner. So given the initial pose and shape, at the first step we optimize only the pose, but here we set the geometrical meaningful user-defined scale factors, which have a large range of values. At the second step, we optimize both the pose and shape, but here the scale factor have a small range of values. At the final step, we optimize both the pose and shape using only the inliers. By this annealing process, the estimation can avoid to get stuck in the local minima and finally produce accurate and robust result. In the experiment, we generate following synthetic data. First, as the outlier ratio is changed, we evaluate rotation and translation errors. As shown in these figures, the proposed PMP method achieved better accuracy than the P3P method. Also, the optimized results have the lower errors than the existing PMP method. In the case of the data with a low outlier ratio, this robust estimation-based method shows their very low errors. But it didn't work in the case of high outlier ratios. Regarding the computational time, the PMP method is very faster than the P3P method. We tested the algorithms when the pitch angle and 2D bounding box are erroneous. As shown in these figures, the PMP-based method gets worse in the large pitch angle and 2D bounding box errors. However, if we utilize the proposed hierarchical robust estimator in the refinement step, we can improve the performance as shown in this figure. We evaluate the method on a virtual simulation dataset. Since the ground truth 3D models are known from the simulation dataset, we did two kinds of experiments. One is pose-only estimation, another is pose and shape estimation. From the below tables, we can see the proposed PMP solver and hierarchical robust estimator achieved the low rotational and translational errors. Similarly, in the evaluation on the KT dataset, the proposed method achieved the best performance. Here we qualitatively compare the existing robust estimator and our hierarchical robust estimator. The proposed method got the more inliers, thereby producing the accurate object shape. We compare the computational time between the existing P3P solver and the proposed PMP solver. We can see the computational time is significantly decreased with the smaller iteration. In addition, we measured the computational time in the Qualcomm Snapdragon processes. The proposed pose estimation method took less than 0.2 milliseconds. To sum up, we proposed a very fast PMP solver for on-road objects, and a hierarchical robust estimator to polish the initial estimate and to be robust to many outliers. In the experiment, we showed the proposed method can be practically applicable for the real-world tasks.